In this lesson, we're going to talk about dissociation in solute concentration. Specifically, we're going to be thinking about how the concentration of something changes if it dissociates in solution. That means falls apart. Some things it turns out dissociate and other things don't. So before we can talk about dissociation, we need to make sure we're clear on 4 separate categories of compounds. And so here in this lesson, we're going to take a look at the properties of ionic compounds. And ionic compounds, remember, are held together by ionic bonds, and they're made from a metal and a nonmetal. And when we look at a periodic table, remember over on the right side over here, we have our nonmetals. And over on the left side, and all the yellow over here, we have our metals. Okay? The only one that kind of doesn't follow this rule is hydrogen right there. Hydrogen secretly belongs over in that nonmetals category. So besides that, this sort of left-right division of the periodic table works pretty well. Okay, so ionic compounds are made of a metal and a nonmetal. Strong acids we'll also take a look at in this lesson, and they always start with H. So we have ionic compounds, which are a metal and a nonmetal, and we have strong acids, which start with an H. Then we have covalent compounds, which we'll identify because they're made of 2 or more non-metals. So that means they're made of 2 things that we see there circled in the purple. And lastly, we have a category of compounds called weak acids and bases. And here, there's just a few examples you need to know. NH3, HF, and HC2H3O2. It turns out these 2 right here turn out to be acids, whereas NH3 turns out to be a base. And we'll take a lot of looks at weak acids and bases and their properties later in this class. For now, it's just important that you kind of just memorize those are some weak acids and bases that come up over and over again. So I would go ahead and write these down in your notes and just memorize those as examples of weak acids and bases. Okay, now that we know how to categorize these 4 different groups of molecules, let's talk about how they're different in terms of their dissociation. Okay, first thing to know, ionic solids, which are made of ionic compounds, dissociate in water. Okay, what does that mean? Well, here we have a solution. We have water, which is the solvent. And then in it, we place sodium chloride. So down here, we have an ionic compound, sodium chloride. And that's what we're representing here in this chunk of green and yellow ions. The green there would be the negatively charged ion, the chlorine, and the yellow would be the positively charged ion, which is sodium. And what happens when you put them in water, and we've already actually looked at this, is they fall apart. So notice here we have just the negative ion, and then here we have just the positive ion. And so that means what happens to the number of solute particles is they double. So for example, if I put 10 sodium chloride molecules down into water, it's going to split apart into 10 sodiums and 10 chlorines, so we'll have a total of 20 solute particles, okay? And that's what dissociation is. It's the splitting apart of our compound into ions in solution. So dissociation doesn't just mean like it's dissolved, it means it dissociates from each other, it splits apart. Okay, so this happens whenever we have an ionic compound, which remember is a metal and a nonmetal. Okay? Now, it turns out strong acids also fully dissociate. So they're going to split apart in water as well. So once again, we have water as our solvent, and let's say we put 3 HCl molecules down there. Okay, so just 3 molecules of HCl. Notice HCl starts with an H, and so it's an acid. And it's not one of our weak acids that we looked at, which was just HF and HC2H3O2, also known as acetic acid. So that's a strong acid. What happens in solution? It splits apart. How many hydrogen ions are we going to have? Well, we have 3 HCl's, so we're going to have 3 separate hydrogen ions. These 3 hydrogen ions, we'll see later in class, actually turn out to help us calculate the pH of the solution. And then how many chlorines do we have? Well, we have 3 chlorines, and they're all floating around separately, surrounded by water molecules, moving around as these separate ions. So they've fully dissociated. They've split apart. So once again, with HCl, we see that the number of solute particles we have doubles because of this dissociation process. Now, it turns out not everything dissociates. Strong acids and ionic compounds do, but weak acids and bases actually fall in a slightly different category. What makes them weak acids or bases is that they sometimes dissociate. So let's grab one of our weak acids. Let's say we have HF, okay? So here's our 3 examples that you need to have memorized: NH3, HF, and acetic acid HC2H3O2. And we're going to put 3 HFs into solution. What happens? Well, what happens is sometimes they split apart, but sometimes they don't. So, for example, maybe out of the 3 of those, 2 of them stay together as HF molecules, so they haven't dissociated. So what I've drawn there in the purple didn't dissociate, right? It didn't split up. but some things do split up. And so out of the 3 molecules, maybe just one of them splits apart. And so that's what we mean when we say they sometimes split up. Some of the molecules I drop in the water will fall apart and some won't. Now, it turns out, I've drawn here 1 out of 3 dissociating. It turns out that the actual ratio is more like 1 out of 1,000 or 1 out of 10,000. So almost all of the ions in our weak acids and bases stay together and don't split apart. But very occasionally they do. Okay, last category, covalent compounds. They don't dissociate at all. We recognize covalent compounds because they're made of 2 or more nonmetals. Now, just a warning here, technically an acid is 2 or more nonmetals, right? HCl, H is a nonmetal and Cl is a nonmetal. So those acids are an exception here to that covalent categorization process. Or perhaps another way to think about it is they are covalent, but they happen to split up because they're acids. All right, so covalent compounds though don't dissociate. So let's say I put C6H12O6 down in the solution. Once again, let's say I have 3 of them. What happens? Well, we saw that our ionic compounds and our strong acids and bases fully split up. Our weak acids and bases split up some of the time. This never dissociates. So if I put 3 molecules down into solution, I get 3 molecules floating around, but they haven't split up. So they all just stay together. So if I put in 3 molecules, I get 3 solute particles. There's no change there to that concentration because there's no dissociation. So hopefully you can start to see now that if I do have compounds that split up, that changes the concentration of particles in solution. And that's going to be pretty important for some properties of solutions. And so we'll talk about that specifically in future parts of the class. If it's important, we'll mention that, hey, this is when it matters how many particles there are, and we have to think about this solute dissociation process. Okay, let's practice thinking about what ions we have present. Here it says, what is the concentration of each solution when you consider dissociation? So what it's asking for is, what's the concentration of solute particles? How are we going to do this? First, we're going to have to identify our compounds as covalent, ionic, or acids. Okay? Because that will tell us if they dissociate or not. So let's just go through and do that. Well, sodium and chlorine, we've already said is an ionic compound because my sodium is a metal and my chlorine is a nonmetal. And so I'm just going to label this as ionic. All right? C6H12O6, those are all nonmetals. Carbon, hydrogen, and oxygen are all nonmetals. So that's a covalent compound. I go to CO2, similarly, carbon and oxygen, both nonmetals. Now, if you're not able to see that, that's okay. You just need to pick out a periodic table when you're doing these problems on your own to make sure that you can identify them as either a metal or a nonmetal, just by their position in the periodic table, like we talked about earlier. So CO2 turns out then also to be a covalent compound. All right, iron nitrate. Well, iron clearly a metal, and nitrogen and oxygen nonmetals. And so that makes that an ionic compound. All right, and lastly, HCl. So here's where I was saying that if you look at HCl, you would initially categorize it as covalent because you'd say hydrogen, it's a nonmetal, which it is. And chlorine, it's a nonmetal, which it is. And then you say, okay, since it's 2 nonmetals, that would be a covalent compound. But it starts with H. So while it is a covalent compound, it's a special category of covalent compounds. It's an acid. And so we're going to label that one as an acid. Okay, now for those that do dissociate, we're going to write what's called the dissociation equation. So we've done step 1 and we've identified them. Step 2, we need to write our dissociation equation. All we're doing here is we're writing the different ions that come apart when they go into solution. And so here we have sodium chloride, and it's going to split apart into sodium, which is Na+, and chlorine, which is Cl-. So that's the dissociation equation. Pretty straightforward for sodium chloride. Gets a little more complicated when we have multiple ions floating around, okay? Now, here we have sugar, our covalent compound. We don't need a dissociation equation. Nothing happens. It doesn't dissociate. The next one we need a dissociation equation for is D, which is also an ionic compound. Here is where we have to keep in mind what a polyatomic ion is. So here we have NO3, right? That's a polyatomic ion. And so really this could be a tip 4. So let's go ahead and make a tip number 4. Polyatomic ions stay together. So polyatomic ions stay together. Remember, polyatomic ions are ions made of more than one atom, and the NO3 is an example of that. If you ever see parentheses, you have a polyatomic ion. If your ionic compound contains 3 elements or more, you have a polyatomic ion. If you're not familiar with the polyatomic ions, go to your OpenStax textbook and just search polyatomic ions, and it'll come up with that list and a description of what those are. So you may want to check that out. So the polyatomic ions stay together, and here we're specifically told that there's 3 NO3s. So that means the ions we're going to get is 1 nitrate when it goes into solution, and the charge here is going to be 3 plus because there's 3 nitrates, each at -1 charge. That may be hard for you to figure out, and that's okay. The charge is not essential, but getting the number of ions is essential. Okay, and now how many nitrates do we have? Well, we have 3 because of the 3 outside the parentheses. So we're going to put 3NO3 minus. So if you have a number outside the parentheses, that's going to come up front for a polyatomic ion. If you don't, then that number is going to stay at the bottom, and it's just telling you, hey, there's just 1 polyatomic ion, right? That's what the absence of parentheses would mean. All right, now we want to determine the number of ions or compounds present in our solution. What do I mean by that? Well, there we're just going to count how many things we have. So let's do this in a new color. Let's do blue. Here I just have 1, 2. So I'm going to put I equals 2. Turns out that's something called the Van Hoff factor. And we'll look at that more in a later video. But basically, it's just the number of things something dissociates into. Meanwhile, for sugar, C6H12O6, that I is just equal to 1 because it doesn't dissociate or split up at all. It's just one thing. Same for CO2. We have an I of 1. And then for our iron nitrate, how many different things have we split apart into? 1, 2, 3, 4. So we have an I of 4. Okay? Lastly, let's do our acid. First, let's start with the dissociation equation. There we have H and Cl, so it's going to split apart into H plus and Cl minus. Again, relatively easy like our sodium chloride example. And when we go to write the Van Hoff factor, the I, it's going to be 2 because there's 2 things it falls apart into. Okay, now let's go ahead and multiply the concentration by the number of ions. So what are we doing here? Well, remember, if we had 1.2 molar as our sodium chloride concentration, and now our things fall apart into 2 separate pieces, what's the concentration of all those pieces? Well, it's going to be twice as big as it was because now our one thing fell apart into 2. So all I'm going to do is I'm going to multiply it by my I. So that's times 2, and that's going to give me 2.4 molar. Okay, so that's the concentration of sodium chloride when you take into account each separate ion. Okay, so the concentration of ions in that solution is 2.4 molar. For my sugar, I'm just going to multiply by 1. So there's no change there from thinking about dissociation because it doesn't split up. So it's 0.8 molar. All right, now CO2, same thing. That doesn't split up, so it's going to be times 1. So it stays the same at 2.0 molar because it doesn't split apart. Our iron nitrate changes the concentration a lot because our I is 4. There's 4 separate things that come out of that ion when you put it in solution. And so that's going to give you 0.4 times 4, which is 1.6 molar. Okay, and lastly, our HCl, it's split apart into 2 things. So we have 0.1 times 2, and that's going to give us 0.2 molar. Okay, so that's thinking about how different solutions behave in terms of dissociation. Remember, quick summary here. Our soluble ionic compounds completely dissociate or fall apart into ions. Our strong acids completely dissociate or fall apart into ions. Our weak acids or bases sometimes dissociate, maybe 1 out of 1,000 splits apart, and our covalent compounds never dissociate.